In the microscopic realm, survival unfolds without spectacle. There are no grand gestures here, no visible drama, only pressure, only the quiet insistence of chemistry and environment narrowing what can exist, life advancing because it must. At this scale, to persist is simply to replace. To endure is to remain present in the next moment and then the next. No banners mark the struggle, no victories are declared, only replication, only adaptation, and only the steady need to continue. And from this invisible arithmetic of survival, something can emerge that reshapes the world above it. Evolution doesn't move with a blueprint in its hands. It moves like a tide, testing and erasing and leaving traces behind. Changes appear quietly, without intention. Most fade before anyone could ever notice. A few remain, and what remains over centuries begins to look like destiny. Life unfolds this way, through repetition and through difference. A slight shift or a copied mistake or a variation so small it almost escapes attention, and then time does the rest. Among the simplest travelers in this long story are viruses. They are little more than strands of instruction wrapped in protein. They do not grow in the open air. They wait for encounter. For the moment a living cell opens the door. Inside they copy themselves, and in copying they change. Most of these changes lead nowhere. Some weaken and some vanish. But occasionally one fits its moment a little better than the rest. It moves more easily, it persists a little longer, and it finds the next host. Hosts influence viruses. Viruses in turn reshape their hosts. Across generations, a quiet negotiation unfolds. Nothing here intends harm. Nothing plans conquest. There is only replication, variation, selection, again and again across deep time. These behaviors are nothing more than the rules of a game, the game of life. The rules are simple enough to fit inside a few lines of code, but what they set in motion is anything but small. We gather them, translate them into mathematics, and with a single command, we let a new world begin. Imagine a world generated inside a closed simulation, governed by equations. Time accelerates within it, variables adjust, and every interaction leaves a trace. The laws do not change. Gravity holds oceans in place. Thermodynamics disperses energy. Entropy slowly erodes structure. Energy is conserved and transformed, never created from nothing. Heat flows from concentration to dispersion. What takes shape inside the model feels familiar. It echoes home. Oceans settle into tectonic basins while continents shift and collide. Mountain ranges rise and gradually wear down. Forests reach for light, grasslands move with the seasons, and coral reefs build themselves layer by layer. Insects, mammals, birds, and marine life occupy their niches within a web shaped by predation and cooperation. Only then do we introduce a single viral lineage. At first, it barely stands out. A fragment of genetic code moving quietly through a living network. There is no strategy waiting to unfold. There is only replication, and with replication, the possibility of change. The experiment is simple in principle. Allow variation and selection to operate within this structured world and observe what emerges. Under stable physical laws and dense global connectivity, how far can adaptation travel? When guided only by probability, how intelligent can evolution begin to look? At the macroscopic scale, a virus rarely arrives with spectacle. It is nothing more than a fragment of genetic material enclosed within a protective shell, released into the open environment where light, time, and chemistry erase most of what appears. The vast majority disintegrate before anything can happen, and only a rare few endure long enough to be carried elsewhere by currents they do not perceive. In this world, the first viable particle forms in darkness, far beneath the ocean's surface, near mineral fractures where heat and chemistry converge. There is no host waiting and no immediate replication, only a stable structure suspended in cold moving water, held together by pressure and slowed in its decay by the deep. It drifts along the ocean floor as dense currents slide past in slow, indifferent motion, and within the simulation, millions of years pass while it travels without aim or awareness, moving only where the water permits. Eventually, tectonic forces reshape the planet's circulation, altering the pathways of the sea as rising water pushes through submerged caverns carved into coastal stone, drawing the particle upward into a flooded cave where tides breathe rhythmically through narrow corridors of rock. Thousands of years unfold in this dim enclosure, the world outside shifting in climate and structure, while the particle itself remains intact. Over centuries, underground channels extend farther inland, and storm surges force seawater through hidden fractures beneath the terrain, carrying the particle once more through dark passageways shaped by erosion and pressure, inching gradually toward the surface. At last, it emerges into a small, isolated lake set above the shoreline, a basin calm and contained, cut off from the immensity of the open sea, where the long journey from abyssal depth to surface water finally comes to rest. It has not grown more complex, nor has it awakened into intention, yet it now exists within a different environment, one where contact is no longer impossible, and where, at some uncertain moment, encounter may finally occur. The lake remains stable and enclosed, and left undisturbed, the virus could persist there indefinitely, suspended in quiet equilibrium. But this is a simulation, and a single parameter is adjusted. Its outer shell develops a subtle adhesive property, just enough to cling to organic surfaces and resist being lost to the depths. Semi-aquatic rodents begin to visit the shoreline, moving easily between water and land as they feed along the banks and return to their nests inland. The virus attaches to damp fur and narrow paws, and in this simple contact it travels beyond the basin. Most replication attempts fail, and many variants disappear as quickly as they arise. But over centuries, selection favors those that tolerate the warmer internal temperature of a mammalian body and withstand its immune defenses without destroying the host too quickly. Gradually, persistence replaces fragility. As time unfolds within the model, another opportunity emerges. Bats roost in nearby caves and drink from the same waters, gathering in dense colonies and crossing vast territories in a single night. When the viral lineage adapts to this new host, its range expands dramatically. Mobility becomes an extension of survival. The simulation shifts once more, this time not by strengthening the virus directly, but by altering the sensory tolerance of its host. Light sensitivity softens and infected bats begin to tolerate brighter environments, settling closer to cave entrances, exposed cliffs, and eventually human structures. The boundary between night and day grows less distinct, and ecological layers that once remained separated begin to overlap, tightening the network of contact between wildlife and human populations. The virus does not command these movements. It simply benefits from the new geometry of interaction, where encounters become more frequent and transmission pathways multiply. Then a final modification occurs. A minor alteration in surface structure broadens cellular compatibility, allowing the virus to bind to receptors present in human tissue, while early replication becomes quieter and less likely to trigger an immediate immune alarm. The first human is infected, and for the first time the simulation slows, allowing us to follow events almost in real time. Nothing about him announces what has happened. At the molecular scale, a subtle mutation has already prepared the crossing. The viral surface now carries patterns close enough to human tissue that the immune system hesitates, detecting something unusual but not enough to trigger alarm. The response remains measured. In most cases, symptoms are mild. In many, they never come at all. He moves through his day unaware. He boards a train and stands in close conversation. There is no dramatic collapse, no visible signal demanding isolation. And in a world defined by motion, movement continues uninterrupted. He feels almost normal. Maybe a slight warmth behind the eyes, a fatigue he blames on a short night. Nothing that would make him stop. Later, he walks through an airport terminal bright with movement and departure screens, joins a line, hands over a passport, sits among travelers bound for different continents. The world moves, as it always has. In meetings, in cafes, in crowded rooms, he speaks and laughs and coughs once without thinking. The people around him register nothing unusual. To them, he is simply another body in the flow of the day. By the time patterns begin to form elsewhere, he has already become a point in a network far larger than himself, a quiet node in a system where movement never truly stops. The mutation has not rendered the virus invisible. It has made it ordinary. By the time surveillance systems detect a coherent pattern, the lineage is already distributed across continents, circulating quietly within a species whose greatest strength is its connectivity. What began as a single, unremarkable encounter becomes synchronized spread on a planetary scale. And now the simulation no longer accelerates, it watches. Years pass and the virus never truly disappears. It lingers quietly in millions of bodies, never dramatic enough to demand attention, never absent enough to be erased. In laboratories, it is occasionally detected in respiratory samples, appearing stable and non-aggressive before being catalogued and quietly forgotten as life continues. Those who carry it feel nothing unusual. It replicates at low levels along the airways, and the immune system keeps it contained without urgency, settling into a long, silent tolerance. Then the air begins to change. Wildfires burn longer and smoke drifts across oceans. Heat settles over cities. Pollutants linger in valleys and industrial corridors. The atmosphere remains breathable, but irritation becomes constant, a low shared inflammation carried in the lungs of millions. Inside bodies that have hosted the virus for years, the equilibrium begins to shift. For a long time, it remained in a low replication state within the upper airway lining, its activity tightly regulated by the surrounding cellular environment. The immune system did not eliminate it, but it kept its replication restrained. When chronic environmental irritation increases, the biology of those same cells changes. Inflammatory signals rise, and molecules released during sustained airway irritation alter the internal conditions of infected cells. What had been a stable, low-level presence encounters a new biochemical landscape. In this altered environment, the virus responds as if it had been waiting for this signal across millions of silent years. What once remained restrained now shifts abruptly. A dormant segment of its genome activates and replication surges with sudden intensity. Production no longer increases gradually. It accelerates with a ferocity that seems almost pre-written into its long journey. Viral particles spread beyond their original confined sites and begin invading deeper respiratory tissue. The virus has not transformed. The world around it has, and it has changed everywhere at once. The change does not begin everywhere at the same hour. There is no single ignition point, no identifiable ground zero. And yet, within the same season, across hemispheres linked by the same unstable climate, similar cases begin to appear, unconnected but strangely synchronized. Within weeks, hospitals collapse into improvised triage zones as oxygen dwindles and hallways turn into wards, parking lots into morgues. Trains grind to a halt, flights disappear from the sky, and supermarket shelves stand bare, while power grids flicker under staff shortages no system can withstand. Governments continue to speak, but their words no longer alter the trajectory. Across continents, the same pattern tightens like a vice. Cities dim as systems falter, and movement slows to a fragile crawl. Institutions strain under absence, and fear settles into daily life, reshaping borders and trust. The structure of civilization remains visible, yet its internal coherence weakens until coordination splinters and continuity thins to a thread. In laboratories, the response accelerates with historic speed. Platforms are deployed, trials coordinated across nations, manufacturing scaled before final results arrive. Yet the problem is no longer a single lineage, but a shifting landscape of related variants, emerging in parallel across continents. The scale of global transmission feeds continuous divergence, and by the time one dominant strain is characterized, others have already gained ground. The simulation accelerates once more. Decades collapse into minutes and humanity slides toward extinction. Populations fragment, then vanish. The last enclaves fall silent and communication ceases entirely. Within a few generations, human presence becomes so rare that no one can say with certainty whether the species still survives anywhere on Earth. Beyond those shrinking pockets of survival, the virus expands further still. After humanity, it reaches new species, adapting unevenly to each. In some, it becomes rapidly lethal and collapses entire populations. In others, it settles into a persistent presence, reshaping ecosystems without immediate devastation. Predators lose prey, and entire food webs reorganize as the virus threads itself through the living fabric of the planet, sparing some, extinguishing others. Centuries pass. Human presence becomes rare, then uncertain, then almost mythic, a trace in the sediment of a planet that no longer depends on the species that once believed it ruled. What unfolded required no malice and no intention. The virus did not need intelligence, it needed conditions. Generative artificial intelligence systems are now capable of exploring chemical and biological spaces at a scale no individual researcher could traverse alone. Recent experiments have already revealed how easily intent can redirect that intelligence. A generative system designed to discover therapeutic molecules was given a single inverted objective, and within hours, it proposed tens of thousands of compounds predicted to be highly toxic using only public data and ordinary computing resources, nothing classified and nothing exotic. The tools exist, the data exists, the algorithms grow more capable each year, and they wait only to be asked the question. As laboratory automation advances, as genetic synthesis becomes more accessible, as design models learn to anticipate biological behavior with increasing accuracy, the line between simulating a threat and constructing one grows thinner. What once required vast institutional infrastructure now begins with software and datasets. If a model can imagine it, and if the tools to build it continue to spread, then perhaps the next simulation will not unfold behind glass. Perhaps it will begin quietly somewhere real.